Okay, so in this video, I'd like to go through some examples of uh, nucleophilic character of the various organometallic species that we introduced last time. First, by starting with their reactions epoxide electrophiles. And recall that epoxides are very electrophilic because of bond angle strain, and these undergo SN2-like reactions with organometallic species. And an SN2-like epoxide opening is carried out under basic conditions. As we discussed last time, all organometallics in this course, such as Grignards, organolithiums, and organocuprates, are basic nucleophiles. They're good nucleophiles so they attack at the least hindered position, which is fastest for SN2. And any SN2 attack where you push out or break a sigma bond in a concerted step is going to be an anti-like addition, or it's going to be stereospecific. So we'll see that in these examples that follow. Of course, phenolithium has a very nucleophilic carbon-lithium bond that you can approximate as sort of a benzene ring owning a lone pair, which will attack that primary and less substituted carbon of the epoxide much faster than it would attack the tertiary carbon. That's going to cleave the epoxide open to give an alkoxide. This carbon-carbon bond stays intact, and the phenyl group is now attached to the primary carbon. Where the electron density that was between phenyl and lithium is now between phenyl and the primary carbon. Next, you will always work this up with some acidic aqueous solution, and that will give you a neutral alcohol product. And there is no stereochemistry for this example because this one is achiral and lacks stereocenters. You do want to note that these are two separate steps. So step one, add your strong base, good nucleophile, let it react, and then later, after that reaction is finished, you add a strong acid to work it up, okay? It would be incorrect to put phenolithium and hydronium all in the same step because a strong acid would simply quench your phenolithium before the reaction occurs. So the next example is dealing with an organocuprate, where we can basically approximate this organocuprate to be a methyl with anionic-like character, where I'm indicating this carbon-copper sigma electron density as if the methyl is going to sort of own that as a lone pair. So it will attack the less hindered secondary carbon faster than it will attack the tertiary carbon. Once again, we are under basic conditions. Cleaving the epoxide open. And this gives an alkoxide that is anti. Here there are stereocenters, so you must show that your organocuprate adds anti to the alkoxide, which now can be worked up with another strong acid. And that will give this single enantiomer the tertiary alcohol, or specifically hydroxyl from the epoxide and methyl from the cuprate are anti to one another because of the SN2 like reaction. In the final example, we have a highly hindered tertiary carbon and an unhindered primary carbon. And the Grignard can be approximated as if it's an ethyl group that owns this sigma electron density that was between carbon and magnesium. The carbon of the ethyl is going to attack the primary center and break the epoxide open. And the ethyl will add anti or trans to the resulting alkoxide. The stereocenter on the left does not undergo any change. There's no reaction occurring there. But the stereocenter on the right involves the deuterium being sort of pushed up as the ethyl group comes underneath the epoxide. Once again, acid workup gives a neutral alcohol. And once again, the hydroxyl and ethyl are anti to one another. So those are the reactions with epoxides. And let me just make a note, in each of these, that the nucleophilic atom, which I'll sort of circle that nucleophilic group, I guess. It's a carbon of phenyl, a carbon of the methyl, and then a carbon of the ethyl. Those nucleophilic atoms are at these relative positions in the products. And you can see that it was an epoxide that was opened up because you have this 1-2 relationship that results. The carbon that has the new carbon-carbon bond is 1-2 relative to the alcohol. Here it's 1-2, or vicinal, and this one is also 1-2. So when you have a new carbon-carbon bond that is one away from an alcohol, or vicinal to an alcohol, that means you open an epoxide in that synthesis. Okay. So now we'll do reactions with carbonyls, the aldehydes and ketones. Once again, the carbon-lithium bond of butyllithium is very nucleophilic. It can be treated as an anion, and that carbon will attack the carbonyl and break the pi bond. So we get a nucleophilic addition reaction here. And that electron density that was between carbon and lithium is now between two carbons. So we added the 4-carbon butyl chain. Acid workup, once again, will give a neutral alcohol in a later step. So starting with this aldehyde here, the product is a secondary alcohol. And this would be a racemic mixture where you could attack from the top or the bottom of that planar carbonyl. So the next example has two electrophilic starting materials. There's a ketone And the methyl of a Grignard could attack above or below that ketone, generating a diastereomeric mix of the alcohols. This ether here stays intact. We know that ethers are inert towards organometallics, and that's why they are great solvents for organometallics. Or they're non-reactive. And let me amend this. You would still have the O minus with a magnesium bromide cation next to it before the acidic workup is done. However, this compound also has an epoxide. And the Grignard is going to react with any available electrophile, or you should always assume it's an excess. And it will continue to react as long as there are electrophiles that are sufficiently electrophilic for a Grignard. And there are two carbons of the epoxide. One is secondary, one is tertiary. So under basic conditions, of course, it's going to attack the secondary carbon, the least hindered of the epoxide, and break that open. And here the methyl will attack from underneath the ring, anti, to give tertiary alkoxide, which of course would also sit next to magnesium bromide. Anytime I draw an anion, there's always a cation that's closely associated nearby. However, after the acid workup, now we are going to simply protonate both alkoxides to make two tertiary alcohols. And if I want to define some stereochemistry, you could have the methyl attack the ketone from underneath, which would push that carbonyl up as an alcohol. Or you could have the methyl attack from the top of the planar ketone, pushing the methyl down, or sorry, the oxygen would be pushed down. So that gives a diastereomeric mixture. Okay, so what I want to do now is go through some examples of how we use these organometallics along with the appropriate electrophile in synthesis. And a very solid hint that you need to make an organometallic and then use it to make a carbon-carbon bond is when you see that a carbon-halogen bond, like this carbon-bromine bond, has been transformed into a carbon-carbon bond. So CX, where X is a halogen, going to CC is a hint of an organometallic. And in many cases, especially when we use epoxides, you have options of which organometallic to use. So what I see here is that I have a ketone. And a great way to prepare a ketone is to make it from oxidizing a secondary alcohol. And this oxidation can be done with any weak oxidant, such as PCC, in a non-aqueous solvent like DCM. So from there, it's more clear that the carbon of my initial bromide that can be made nucleophilic is here. And the carbon of the epoxide, or sorry, the alcohol that came from an epoxide is one away, okay? Or there's this 1-2 relationship here. And that tells me an epoxide intermediate. So now I'm going to think back to when I had that alkyl bromide, I could easily turn that into a carbon nucleophile by adding magnesium and the appropriate ether solvent. Okay, you could also do this reaction by making an organolithium or by making a dialkyl cuprate. They all react with epoxides in a basic manner. And then the 3-carbon epoxide that I need is this, propylene oxide, where the primary carbon here, or what was primary, is attacked, and the secondary carbon keeps the oxygen. And after we add the epoxide and let it sit for a minute, you would add some hydronium in a later step. So next, let's do one where we have to use a carbonyl. So in this problem, I see that the carbon of benzyl alcohol has been transformed into a different alcohol. In other words, there are 2 hydrogens on this primary alcohol, and now there's a single hydrogen at the secondary alcohol, which means that oxidation has occurred because we have decreased the number of carbon-hydrogen bonds. So I'm going to go ahead and oxidize that in the first step with, once again, a weak oxidant like PCC, which will take off a single hydrogen from the alcohol, carbon, and oxygen to give an aldehyde. Thus, it has been oxidized from +1 to +2. You can visit my alcohol oxidation video if you are unsure of the meaning of these oxidation reagents and or reactions. But now that we have the aldehyde with an electrophilic pi star, we can treat it with the appropriate carbon nucleophile to make the secondary alcohol. And we need a 2-carbon, 1,2 ethyl nucleophile, like a Grignard, or you could use an organolithium, or you could use a dialkyl cuprate. They all react with aldehydes. After that reaction occurs, you get nucleophilic addition, and then acid-base during the workup will give you the secondary alcohol, where this carbon of ethyl Grignard has now made a new carbon-carbon bond there. Okay, so 2 more examples, and these are a bit more involved. So what I see is that this carbon of the bromide now is participating in a new carbon-carbon bond. So that means we're going to turn that into some type of organometallic at some point. Maybe a Grignard. And I also see that my ethyl group is likely at the terminal end of the structure, which by process of elimination means if these are my only carbon sources, then these 2 carbons of the epoxide, which are identical, must be those 2. So now what I can do is start to build this carbon chain. I'm going to do it retrosynthetically. So what you have first is a secondary alcohol. And that secondary alcohol could originate from an aldehyde electrophile being attacked. with the appropriate organometallic, such as a Grignard, ethyl Grignard, or ethyl lithium, or even the cuprate, followed by an acid workup, where we see that the carbon of the aldehyde is directly bound to the carbon of the Grignard in the product. So that's a nucleophilic addition to a carbonyl. However, you would have to show how you made that organometallic. If your only carbon source is ethyl bromide, you would turn that into ethyl magnesium bromide by adding magnesium 0 and some ether solvent. Alternatively, you could use 2 equivalents of lithium in a hexane solvent, and that would give your organolithium. So now we need to build this aldehyde compound from the starting material. And that's clearly going to come from putting the ethylene oxide together with the cyclopentyl bromide. And I know the epoxide is an electrophile, so let me make the bromide into a good nucleophile. So I'm going to go ahead and add, I'll do the organolithium for this one just to show you. 2 lithium equivalents in hexane. That's going to give me the organolithium, which can then be treated with an epoxide, ethylene oxide, followed by an acid workup. Where this carbon is now nucleophilic, and it can attack either carbon of the epoxide, it is symmetrical, to give me a new alcohol product. Or the new carbon-carbon bond we have built is between those 2 carbons. But once again, here we get this 1-2 relationship, where the new group, the carbon chain that was nucleophilic, is 1,2 to the alcohol. Finally, if you need to turn it into a carbonyl, which can undergo further nucleophilic addition, then you need to oxidize that primary alcohol to the aldehyde with PCC. So a lot of these reactions involve addition to an epoxide or a carbonyl, followed by oxidation of the resultant alcohol to another carbonyl, to which you can then undergo another addition. So the final example I want to do here involves the oxidation of an aldehyde to a ketone and the transformation of an alkyl bromide to an alcohol. And once again, I notice that this carbon halogen bond has been turned into a carbon-carbon bond, where you have a 1 carbon elongation. So I need to make that into an organometallic. But there's a problem, that I have acidic protons in my starting material, which means those would quench any organometallic as soon as it is made. So before you make an organometallic, you must turn this secondary alcohol into a functional group that can be protected from reaction. And that first involves oxidation of the secondary alcohol to a ketone with PCC. Once it's a ketone, you can then use any alcohol, but specifically diol like ethylene glycol or propylene glycol, with catalytic strong acid to allow for ketal protecting group to form. For more information on this, you should see my video with condensation reactions of aldehydes and ketones, where we generate acetals and ketals. But during that reaction, you eliminate water. And the water comes from each hydrogen of the diol and the carbonyl oxygen. It's condensation. The acetal and ketal protecting groups are stable to base, which means you can make that reagent as basic as you'd like. It's not going to react with itself. So I'm going to now make a Grignard. Which can be treated with the appropriate electrophile. In this case, I just need one carbon. And the one carbon electrophile that can undergo addition from a Grignard is a one carbon aldehyde, formaldehyde. If you work this up with acid and water, then the acid and water will not only put the proton on the alcohol, okay, but it will also deprotect or reverse the ketal, because water was a product during the ketal formation. So if you add water back, it goes backwards to the ketone or deprotects. So those are some examples of reactions using organometallic nucleophiles along with carbonyl and epoxide electrophiles. And they're very important for forming new carbon-carbon bonds. But you should remind yourself of some other synthetic transformations that may be needed along the way, like oxidation or like protection of various functional groups. So remember what the limits of the organometallics are, and that they are strongly basic. And if you have anything acidic like an alcohol, that must be protected before you go on to do subsequent transformations.